Hello and welcome back after the coffee break. I hope you enjoyed the discussions you had out there. And I also hope that the next session will give you a lot of material to discuss about in the next break during lunch. It's my great pleasure to introduce you to Frank Seider. Frank Seider has been with Microsoft for 15 years. 13 years of that he spent with Microsoft Research in Asia. Frank is the only principal researcher I know at Microsoft Research who has not completed his PhD. Instead, his credential comes from the very exciting work he has done around neural networks and especially deep learning and speech recognition. In fact, he and his team were the first to demonstrate how well deep neural networks could work for speech recognition. So this has started a huge flurry of research in that area. Today, Frank will give us an update. He will tell us about the project that his earlier research on speech recognition has evolved towards. He will be introducing the toolkit CNTK. Give me a hand and help welcome Frank and his talk.
Thank you very much, and thanks everybody for being here. So I will talk about deep learning, and specifically about learning deep neural networks with CNTK, which is the computational network toolkit of Microsoft. Maybe you know that Microsoft was one of those early pioneers of deep learning. We were sort of part of the first wave after Geoffrey Hinton has first shown how to reliably train deep stacks of networks. And nowadays, deep learning is pervasive in the whole company. It's basically in Bing, for example, speech recognition, relevance, Skype translator, you heard about that already, HoloLens, and many projects in Microsoft Research use deep learning in the company. So just to give an idea why that is such a big deal, let me start with a slide. This slide shows you the historical development of speech recognition error rates. So my background is speech recognition, so I'm most familiar with this. And this was compiled by the American government. And one of the scenarios that's very important is this curve here, the switchboard scenario, which is about transcribing general topic conversations between people on the phone. Now, why would the American government be interested in that is a different question. But what you can see is that it plateaued around this time. And so it turns out in 2010, my colleague Dong Yu in Microsoft Research in Redmond showed that you can actually get very nice gains with deep neural networks on speech recognition. And I started to collaborate with him, and we were able to basically take this scenario here and push it down from a word error rate of something like 24% to 14%, just by a single technology that we added to this by using deep neural networks. And now we're approaching 9, 8, so we have a real chance of reaching human accuracy, which is measured to be at about 4%. So let me just give you an idea on what that means to have a speech recognizer that runs at about 8 to 9%. This is a demo that our former corporate vice president gave 4 years ago in China, in Tianjin. And what you will see is him speaking, and this will be transcribed live by our speech recognizer that is deep neural network based. Could you please click on the video?
In just the last few years,
just read along.
The combination of statistical techniques and big data have allowed us to do a much better job than we previously were able to do in being able to translate web pages or other kinds of information into other languages.
Okay, so you can see that this is really, really accurate, and this was live on stage, and the speech recognizer was in no way adapted to this specific task. So the one thing that we then did on top of that, once you get speech recognition that is so good, you can start combining it with other things. And what we combined it with was with an automatic translation system. Could you please play that video?
But this technology is very promising.
用这个技术很有希望。
And we hope in a few years that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
So this was the system that then evolved into Skype Translator. And indeed, within a few years, we did break down the language barrier between people to quite some degree. Another important result we had with deep learning was the ImageNet competition. So you can see recognizing or tagging images is an extremely difficult task. If you go back to 2010, we were at error rates of something like 28%, and that has come down basically by an order of magnitude by today, just through the use of deep networks. And this is a system that was developed by my colleagues in MSR Asia in Beijing, and was able to win basically the first rank in all 5 categories of this particular competition. So deep nets are a really, really big deal for Microsoft, and I think for many of you as well. So what I would like to do today is to talk about CNTK. What is it? How would it look like if we were to use it? What's the typical things you need to do? Give you a feel for that. I want to do a deep dive into some of the interesting technologies that we have in there that maybe other toolkits do not have. And if we have some time at the end, I will also show you a couple of examples on concrete examples on what it looks like. So let's start with what? I'm going to first read that to you and then explain it in more detail. So CNTK, you heard this morning, is Microsoft's open source cross-platform toolkit for learning and evaluating deep neural networks. CNTK expresses arbitrary neural networks by composing simple building blocks into computational networks that can be very complex. And it is production ready. So let's start with the first point. So CNTK is Microsoft's open source cross-platform toolkit. So this is kind of interesting. CNTK is developed in an open source model also inside the company and outside the company. And the tool originally was created by my colleague to make our work a bit easier and create more flexibility for our research about 4 years ago. It was open sourced about a year ago to Codeplex. And then the beginning of this year, we moved it to GitHub with a more permissive license. So this is now licensed under the very permissive MIT license. So nearly all of the development we're doing is in the open. You can see all the work that I'm doing there. It's just in some branches. There's nothing hidden. And this is today used by Speech, Windows, HoloLens, for example, Bing, MSR. And many of those contributors in those teams started out as a sort of bottom-up activity. They got interested in it, tried it, and now some of them have evolved into, at least temporarily, full-time contributors to the CNTK project. And the first CNTK-trained models are now at a point where they are still being tested, but they're receiving real traffic from users on Bing, for example, or Speech. Very important, I guess, for you is that it works on Linux, not just Windows-based. Linux is a first-class platform for CNTK. In fact, our main server farm that we use internally is running on Linux. So I do the software development on Windows, but if I want to run a bigger job, I submit it into a farm that is running Linux. Okay, so the next point. CNTK expresses arbitrarily complex neural networks by composing simple building blocks into what we call computational networks. So what does that mean? Let's go through an example. This is sort of the, I would say, the canonical deep network. It's deep because it has more than one hidden layer. So it takes an input, you multiply it with a matrix, add some bias, and run it through a nonlinearity, in this case, the sigmoid. That's your first hidden layer output. You take that as an input to a layer of the same structure, get a second layer output, and use that as an input to a softmax function with, again, another affine transform here. And what you get is a probability distribution over classes that you would like to classify. So what you also need to do is you need to define your training criterion. So typically we use cross-entropy, which essentially gives you a measure for how well your probability distribution represents the correct answer. And then you have to sum up over this criterion throughout the entire corpus, and that's what you're maximizing for. So maximizing means you're adjusting these parameters so that this value becomes maximum. So to turn this into a CNTK computational network, the first thing we need to do is to turn it into our representation. So you can see this is the way you write it in CNTK. It looks very similar to the original math. And then we will translate this representation into a computation graph. So you see exactly the operations. You have an input, it gets multiplied with a matrix, you add a bias, you apply the sigmoid, and so on, right? And that is what we call a computational network. So in these networks, all the nodes here are functions that are applied to data, and the edges are values. These values in CNTK can be arbitrary rank tensors, and we also support sparse tensors for sparse input data for text workloads and the corresponding labels and for embeddings. So one this graph representation has a bunch of very, very good properties, very helpful properties. So one is that it provides you with automatic differentiation. So what does that mean? Well, the way to train those parameters is to basically run data through the network and look at what the output is, and then sort of kick against the model a little bit to make it better the next time it will see the same data. More correct, more close to the correct answer. So for that, you're computing a gradient with respect to the objective function, and then add this gradient to these 6 parameters in this case. And the nice thing is, so actually a hard thing, if you write those kind of things for yourself, is to get those gradients right. But by this representation, all you need to get right is the gradients for the individual nodes, and then you can use the chain rule to compute any gradient by just backpropagating gradients through this network. Another thing is that the graph represents what we call a deferred computation. So in some toolkits, for example in Torch, all the operations you're executing are running right away. In our case, this description gives you this graph structure, and that has a couple of advantages. So for example, this graph structure is then handed to an execution engine that performs the computation. And that means we can do a lot of things, interesting things like optimizing execution and also optimizing memory. And I just want to give an example of what the memory optimization would look like. So if you look at this graph, each of those nodes carries memory for its output, for its result that it computes. And this memory needs to be kept around in some cases because when you're backpropagating your gradient, you sometimes need those values one more time to compute your gradient. That is the case, for example, for the matrix product and for the sigmoid. However, the plus here, that operation does not need the original value to propagate the gradient. So we don't need to keep it around. And by being able to look at this entire graph, we're now able to see and say, okay, this plus and this plus and this plus, they can reuse the same memory. Well, that's a big deal. If you go further, when you're actually using the network as opposed to training it, you don't need to keep anything around for the gradients. So here you can get away with 2 buffers. You always just need the output and the next result, and then you can reuse this buffer here and so on. So it becomes very, very memory efficient. The same thing when you do backpropagation. The gradient that flows through here, you literally only need 2 buffers in this example that just are used, exchanged, one after the other. So this typically gives you something like a factor of maybe 1/3 or half reduction of memory usage, which can be a big deal. Also, because we have an explicit representation of the graph, we can do neat tricks like editing them after the fact, which allows you to do something like a layer building training, where you start with a small network and then keep adding things to it. So this computational network is really the core of CNTK. And so basically by having this Lego-like composability, you are able to support a wide range of standard network types, like feed-forward DNNs, recurrent networks, long short-term memory, convolution, DSSM, deep structured semantic model, and sequence-to-sequence model, and most of them are just composed out of primitive blocks. And it also, well, you can use these applications then, these networks in many different applications, including speech, vision, and text. And you can also combine them. For example, you can do image captioning with this. Okay, computational network. Now, the last point is CNTK is production ready. So what does that mean? Well, CNTK is not just a research tool. It's also meant as a tool for product groups to build the actual products. And if you build products with neural networks, you're dealing with very different dimensions. So for example, the Skype translator model was trained on 1.4 billion samples. Now, try to do that with Theano or something like that, right? So this is very tricky. So CNTK really is optimized for being able to handle very large workloads. For example, of course, we make use of GPUs. But another very important thing is that out of the box, you get algorithms for parallelizing training over multiple GPUs and multiple servers. So here's an early benchmark that we ran. That was done in December. So these versions of the other toolkits are from that time frame. They might have improved. We haven't rerun this again. So what you see is the blue column here is a comparison, was that a standard feed-forward network of 6 layers or something like that, 4 layers. And you see that CNTK on a single GPU is about on par with Torch and Caffe. But the moment you go to multiple GPUs, it scales much better, right? And then if you go across multiple machines, that is something that those toolkits do not support, or in case of TensorFlow, did not support at that point in time, whereas CNTK still gives you very, very nice scaling here. Okay. So now I would like to talk a little bit on what would it look like if you wanted to use CNTK in your work. So the first thing you need to get an idea of is the general architecture of CNTK. So you can see there are three main building blocks. First, you need to be able to read your data. Second is you need to describe your network. And third, you need to run the learner, the SGD learner, over that. So in order to run a CNTK job, you need to basically run an executable and give it a configuration file and a couple of extra parameters that you could also put into the config file. And what you can see here, for example, you say that it's supposed to execute a sequence of actions, and then for every action you have to have a corresponding definition block. So for example, the train action, well, you tell it what GPU it should run on. In this case, pick the best. You give it where the path where the model goes, and then you have configuration blocks for the three components: the reader, the network, and the learner. So the reader has two purposes. One is it reads your data and it interprets the binary file formats that you typically have. For example, there are readers for reading JPEG images or speech features. Another important thing that the reader does is randomization. Now, for SGD, you need to randomize your samples. It's very, very important. But when you're dealing with 1.4 billion samples, that's a tricky business. You don't want to always have to pre-randomize your data if your data is maybe half a terabyte large or something. It's going to be very inconvenient. So what CNTK does, it gives you an on-the-fly way of randomizing the data. And it does that in blocks, so we are still disk efficient. We don't keep sending the disk head running back and forth on the disk all the time. And you just get that for free. Just configure it, and then you get basically the randomization automatically done for you. The next thing is the network. So what do you need to specify? You need to say what are the inputs of the network, what is the network function, including the learnable parameters, and what are the outputs you're looking for. And these networks are described in what we use this kind of silly name for. We call them brain scripts, because they're sort of little scripts that describe what our little brains are supposed to compute. And we have a custom description language for that. We also call that brain script. But not everybody likes to use new languages, and people sometimes prefer to stay in their known world. So we're actively working on making the same functionality available from Python, C++, and .NET languages. That's going to land in 2 or 3 months. So what would that look like? So you already saw this network here and what the corresponding formula looks like, but you need to do a little bit more. For example, you need to define the inputs. So this simply says that this is an m-dimensional input. Now, what is m? You need to tell it, right? Maybe a 40-dimensional feature vector, and you have 9,000 output classes. That's typical for speech. And then you also have to declare the learnable parameters. So in this case, it's a parameter of n by m, and so on. You need to do this for all the layers. Now, that quickly becomes sort of unwieldy. For example, the ImageNet network that I talked at the beginning, that got 3.5%, has 152 layers. So you don't want to write this. So the next thing you can do is you can create reusable blocks. So this is a reusable block that defines a parameter and then directly performs the corresponding network operation. And then you can use those down here. Right? So you pass it the inputs and the corresponding dimension, and notice you can actually also pass functions around. Now, that's already making life a little bit easier. But the next thing you can do is leverage the fact that these functions can be used recursively. So you can actually define a function that defines a whole stack. So for example, L is the number of layers. If the number of layers is 1, then it's just the same as the other macro that the other function I showed you. But if you have more layers, then what you would do is you will first create a network of 1 layer less, and then pass that as an input to 1 more layer. And so now you can very easily describe networks of where your length, your depth is basically parameterized. You can easily change that number and change it to 6 hidden layers or something like that. Okay, so this gives you an idea on what it looks like to describe networks in CNTK. So in summary, it uses a very straightforward, easy, understandable syntax. It allows you to create these reusable modules, which is very useful. And that gives you also the possibility of composing things on a rather high level. And soon, again, this will be possible to be done from Python, C++, and .NET languages. So what does this stupid name, BrainScript, actually comes from? Well, on one hand, we think it's a really great name because it perfectly expresses sort of our grand ambition, right, to build a brain. But actually, its acronym more accurately expresses where we are with respect to that vision. Yes. Okay, so just to close this off, the last thing you need to configure is your learner. So, I mean, there's not many things you can configure. You say whatever, you give it a momentum parameter, a mini batch size, whether you want to use things like AdaGrad. Two things to call out is that CNTK allows automatic adjustment of learning rates and mini batch sizes. And the other is, of course, for the multi-GPU setup, you need to configure some things there. Okay, so what's a typical workflow? Well, to train, all you need to do is you run CNTK with a config file, right? You can also, I showed you that already, chain multiple operations together. So that's very easy. Now, if you want to parallelize that, it's very, very simple. All you do is activate, say, parallel training true. Now you better make sure that it picks the GPU automatically, so you don't run all the parallel things on the same GPU. And you put an MPI exec call in front. So this call basically says run on 4 servers, and it runs 4 processes on each server, and the assumption is you have 4 GPUs in each server. So this gives you a 16 GPU run. Very, very straightforward. Now, when you finish training a step, you might want to do some additional manipulations of your network. So you have this ability to edit networks, and then maybe you want to go back, run multiple iterations, build multiple layers. And when you have your final model, you want to use it, and you can apply it in 2 ways. One is you can apply it from file to file. So you read a data file and write out the prediction probabilities. And the other is, so this is another command here, and the other way is you can use it from code. We have a library that you can call from C++. It's called eval-DLL, even on Linux. And the .NET version of that only exists on Windows. Okay, so now I hope you got a bit of an idea on what it looks like to use this. The next thing I want to look into is some of the algorithms that we implement in CNTK that are a bit more interesting and that other toolkits don't necessarily give you. So of course it has the basic features, SGD, the computation network is not an idea that we invented, every other tool has that as well. I already mentioned we have these algorithms for automatic tuning of learning rate and mini batch size, and I already mentioned memory sharing. The 3 things I want to talk about now is the way that CNTK handles time, the way it helps you by packing variable length sequences into mini batches, and I will say more about how the parallel training actually works. And let me point out, the other toolkits, none of them stops you from doing exactly the same algorithms that I'm going to talk about, but you pretty much have to write them yourself. They don't come stock. Okay, so handling of time. How does that work? Let's take our example from before, and let's add a recursion into it, a recurrence into it. Let's create a recurrent network. So the first thing we need to do is introduce a notion of time. So now these samples are no longer independent. They're meant to be on a time axis. And the next thing we want to do is we now want to feed the output of a network back as its own input, but the sample from the previous time step. So this is what a simple recurrent network looks like. So in CNTK, we do this slightly different. We actually do not have an explicit mention of time here. Instead, we can refer to a past value by an operation called past value. So there's no explicit notion of time. You're not supposed to write any for loops or something like that by yourself. So how does it work? Well, let's take our network again and turn that network into this one here. But first, I need a bit more space. If you now add these things in here, this is what you get. You get these little local loops here. And what you see is suddenly now this network has a cyclic dependency inside of itself. So CNTK has an algorithm to discover those cyclic dependencies, basically the minimum cycles that you have in there. And then CNTK will know that that is the part that has to be unrolled in time, because one frame depends on the previous frame. Everything else that is still drawn, that is drawn in black here, does not have that time dependency. And that's very important to know that, because that allows us to compute all of those in parallel. And doing things in parallel, if you're working with GPUs, is the most important thing to get efficiency. So you really, if you have a chance, want to launch, I'm sorry, I'm pushing the wrong button here. You really want to launch, for example, this part of the operation as a single CUDA launch. Whereas here, you really have to do this step by step, you have no choice. And that can give you a factor of 2 or something like that of speed, at least. So now, if you compare that, for example, with TensorFlow, and TensorFlow does not have this automatic inference. Instead, you literally have to write a for loop where you say your new output and state is equal to, for example, in this case, an LSTM of your previous state. And that's a very weird way of doing it, because you're mixing the idea of imperative code for unrolling and deferred code execution for the final graph. So in a sense, you're generating code here. And in CNTK, you don't do that. Everything is done in a deferred fashion. The loop itself is part of the deferred computation and is open to all the optimization and everything that we can possibly do. So another thing is, well, when you run this recurrence, it means you have one frame, you have to multiply it with a matrix, then you can compute the next time step. You have to multiply it with a matrix again. And typically, these matrices are so small that GPUs are not efficient. You're not actually using most of the GPU cores that you have available. So one thing you can do about that is to batch multiple sequences together. So for example, you're computing maybe 20 sequences together. So in every single time step, you're computing 20 frames in one go. That already makes a huge difference in terms of efficiency. And so in order to do that, CNTK will help you to batch these sequences together into mini batches. So let's just walk through. Let's say we have a total mini batch of, I don't know, 7 sequences, and we start with sequence number 1. Now we add the next one. Yeah, we can put it here. And now you can see this first frame already allows you to execute 2 time steps or 2 samples at once. But the next time step has to be a separate launch because it depends on the previous time step. OK, now we have a bunch of more sequences. Aha, so look, sequence 3 actually is short enough that you can actually utilize this part. And you can also compute this in parallel with sequence 1. Let's add a bit more, sequence 4, 5, and 6, and maybe you have a short one. We stick it in here. And now we're done. We cannot fit any more data, so the rest basically becomes sort of padding. And CNTK will help you to create exactly that structure. Now, there's a couple of interesting things. If you want to launch a parallelizable operation on this, you can just take the structure, flatten it into a matrix, where basically each of those things here is a column, and do a big CUDA launch, for example, to compute a sigmoid, now, or the softmax. Now, this big CUDA launch will also operate on those padding areas here, but it's garbage in, garbage out. We don't quite care. It just runs over it and computes garbage for those padding areas, but we never look at them again, so that's totally fine. But how about the recurrence? So for recurrence, we have a problem. Let's look at this time step. Here, this one, we can do all 4 in one go. When we now go to the next time step, we have a problem, because at this point, we must make sure that we don't carry over the state from the previous sequence. Instead, we need to reset the state. So CNTK has all the logic built in to handle that correctly for you. The same thing is in backpropagation, right, for the gradient. And the third place where you need to make sure is when you're doing a reduction over the whole mini batch, that you don't accidentally include the garbage that has been accumulating here during the processing. So again, CNTK does all of those things for you automatically. And yeah, we really get the automatic speed up. Typically, if you go, say, from 1 to 20 parallel sequences, you nearly see a speed up of 20. And that's because with one single sequence, you very, very rarely utilize your full GPU. If you go beyond 20, 30, that's just a rough rule of thumb, you will not see any further speed up, because at some point you start using your GPU properly, right? But at least to get to this point, CNTK will just do it for free. OK, so recap. Users never explicitly talk about time or see time except using these relative past value and future value specifications. And those are sufficient to infer the complete loop structure of your network. And CNTK does the automatic packing for you as well. Okay, and if you know, some other toolkits do this in a different way because they are not able to pad and pack these sequences together, so they use a technique called bucketing. What you do there is you're grouping sequences of similar length into mini batches, but they should be close enough, and because they're not able to put multiple sequences back to back. And in CNTK, you don't need to do that. Okay, so the next technology I want to talk about is data parallel training. So that's a big deal. That's really a big deal. I just want to give an example. When we built the Skype translator model, we were able to gain another 28% relative word error reduction by using a very specific kind of recurrent network. That's on top of the initial numbers that I showed you. But it turns out that gain only materializes when you run this on the full 1.4 billion samples. If instead you use a smaller set, like this switchboard set I talked about in the beginning, that's only 250,000 samples, the gains are much smaller. It's only 4% relative. They're so small that you would think, that's actually not important. I'm not going to look at that any further. So it was very important for us that we were able to run this line of experiments on the full 1.4 billion samples. Otherwise, we would have never discovered this, that this technique really works that well. And so being able to parallelize your training is not only important to build products fast, but it's also important to have this research cycle and optimization cycle and be able to do that on basically production-sized data. And that is really, really critical. So the way that CNTK parallelizes is, we call it data parallelism. So imagine you have a mini batch of 1,000 samples, 1,024. You have 16 workers, then every worker will grab 64 samples and process them. And at the end of the mini batch, now they have to exchange these partial gradients that they have computed. And the problem is that these gradients are big. That's very, very expensive. So let's do a little bit of a calculation. So for example, for a mini batch size of 1,000, a model with 160 million parameters, it takes about 1/7 of a second. That's maybe a slightly older generation of a CUDA card, it's K20, I think. It takes about 1/7 of a second to compute this. But how long does it take then to exchange the gradient across machines? It's about 1/9 of a second. It's in the same order of speed, right? So that means the communication cost totally dominates, and you cannot parallelize that. You can only parallelize the first thing. So even if you parallelize that thing, make it 10 times faster, your total time, your total speed will not be, the speed up will not be more than a factor of 2, because you're totally dominated by, the time is totally dominated by this communication cost here. So that's the thing, that's what makes parallelizing neural network training very, very hard and non-trivial. So how do you approach this problem? Well, there's two things you can do. One is you can say, well, I just communicate less data for every exchange, maybe some form of data compression. The second is, can we communicate less often? Both of these approaches are used in CNTK. So the first technique is something that I developed. It's called 1-bit SGD, and that's a very interesting technique. So what you do is you quantize those gradients before you exchange them, the gradients that each of the workers have computed. And turns out you can actually quantize them very aggressively if you use a very specific trick. You can quantize them down to a single bit. So instead of having to send 32 bits, you only send 1 bit. But the trick is, that is very important, the trick is this. When you quantize so aggressively, you're making a lot of error there. So some of the gradients are too small, you're overestimating them. Some important big gradients, you're transmitting only a small part of that, because you can only transmit 2 levels of value, basically. So what you do then is, well, you know what the other side will receive, you know what you wanted to send, and now you compute the difference. This is the error that you have not sent yet. You remember that, and then add it into the next mini batch. And then that next mini batch has a chance again to transmit some of that, but is also again quantized to 1 bit, so you have this continuous residual that always carries over what it has not transferred yet. So in the end, you will always transfer everything with full accuracy, actually, but just at a certain delay. You never transmit everything at once. It turns out this really gives you literally a 32 times reduction of communication cost, and that now you can imagine, right? Before we had 1/9 of a second. Now it's 1/9 divided by 32. Now suddenly the whole equation works out and you can get very nice parallelization gains. The other thing we also do is maybe we can communicate less often, and that is we can increase the size of the mini batch. So we have this technique that once in a while tries and see what happens if I just double my mini batch size. Does it still give me similar or same convergence? And it tries that on a small subset. And if it works, it just continues with that big mini batch size. And it turns out in the beginning you start maybe with a few hundred samples in a mini batch, but very quickly it goes up to a few thousand. And at the end of the training you're at 100,000. So communication cost basically completely disappears as a problem. Now, there is also a recent technique that we have just, I think, committed 3 weeks ago to the master branch. It's called block momentum, and that takes this idea a bit further. Of course, the ideal situation is if you don't have to exchange the gradients after every single mini batch. So imagine you just run maybe 300 mini batches in a row, and then you sort of aggregate this block gradient, this master gradient, that basically is the difference from where you started and where you are, but going through some complicated nonlinear path. And if you do that on maybe 16 parallel workers, you can then take these block gradients, aggregate them over all machines, and you get a really big gradient that you can then apply to this initial model. And if you do that, you will immediately diverge. It's not going to work. But we can take a lesson from something called model averaging. Model averaging is pretty much the same technique, except you're not summing up those gradients, you're averaging them. And it is well known, if you average them, actually you don't diverge. So it's just a problem of the magnitude of what you're adding. Now, model averaging is kind of bad because you're making very little use of the actual gradient that you're computing. So the idea of block momentum is this. You first do what model averaging does. You only add maybe 1/k, if k is the number of workers. You only add 1/k of your gradient to your model, but then you remember that you have not yet added 1 minus 1k of that gradient and put that into an error residual, just the same as for the 1-bit technique. And then use this in the next block update. And if you do that, you get very nice convergence, and it works very, very well. And so here is a couple of numbers. So for example, this graph shows scaling over GPUs. This is the number of GPUs. And this is the scaling factor, speed up that you get. And we can look at the red and the yellowish, or what is this actually? This color, greenish column. So the reddish is the 1-bit technique, and the greenish is the block momentum technique. And you see it's always slightly better. And in this experiment, the person who did this, my colleague Yongqiang, he didn't even go further with the 1-bit technique here. And you see you get very nice scaling. You scale 54 using 64 GPUs. Now, at the moment, we're not really using block momentum as a default technique because it's too fresh. We still need to gain a bit more experience on does it really work very, very reliably on a broad range of techniques. But definitely for speech, you can see how it works. If you start with a single GPU baseline of 11% word error rate, both 1-bit and the block momentum technique here, they don't really harm accuracy at these speedups. Okay, so the last thing I would like to do is go through a couple of examples. So I want to start with this ResNet. This is this model that gave us 3.5% image classification error rate. That model has 152 layers. And the basic idea here is that the authors of this paper changed what they tried to learn in a layer. So you're not trying to learn anymore a layer that transforms an input to an output, but instead your default is that you just pass on your input, and you only learn sort of a small correction term. And that gives you very, very nice convergence properties because your gradients really propagate through the network very, very, very nicely. And this way you can really go ultra deep. In this case, 152 layers, and this is how that team won this competition in all 5 categories. So what does this look like in CNTK? So this is the actual structure that was used. It's basically a 1-by-1 convolution, 3-by-3, 1-by-1 with a bigger feature map. And then you add the original input to it, and after each of those steps, you have a ReLU nonlinearity. And the translation to CNTK is really, really straightforward. Right? So you have this function here, which takes the inputs, dimensions, and this is the 1-by-1, 3-by-3, 1-by-1 convolution. So now what is this conv_bn layer? It's one of those reusable blocks that you write yourself for this. And it basically defines a parameter and then executes this convolution primitive that we have. And then it's followed by a batch normalization layer, which is something you write yourself. It basically has, you define the parameter, and then you call the batch normalization primitive. By the way, these two, convolution and batch normalization, go straight into the NVIDIA library, so they're really, really efficient. Okay, and once you have this, the next thing you can do is the same trick, build a whole stack, because we need to build a lot of stacks of networks here, right? You don't want to write this all out, so you use the same trick with a recursion, then with that building block, this is the top level of description of this ResNet. Very, very straightforward. Okay, so recap, convolution, pooling, batch normalization is all standard operations, and it's very straightforward to describe even a 152-layer network in this. I mean, obviously, I just showed you how to program, right? This is nothing super special. All the other toolkits can do this as well, but I just want to give you a feeling on what that looks like in CNTK. Another thing is a technique that recently gets a lot of traction. Is called sequence to sequence. So what this technique does is it maps entire sequences, for example, an English sentence, to another sequence, for example, a French sentence. These sequences don't even have to have the same length, right? So it's very different from the previous RNN that I showed you. And they normally run your input sequence through an encoder network, which is a recurrent LSTM, for example, that creates a sequence of hidden states for every input. And then to generate the output, they run another decoder, a decoder network. And then there is something between, it's called the attention model, that models on what input token is the one that is most relevant to generating a specific output token. So especially in machine translation, they're not necessarily always in the same order. Right? You have the problem of word reordering. And so also, in order to run this model, you need to use a technique called beam search, which maintains multiple hypotheses and only picks the best at the end of the sentence. And all of this can be described just by CNTK using the computation network. And we ran this at the moment on a small task for letter-to-sound conversion. We didn't run yet machine translation in this. So it translates a letter sequence into the corresponding phoneme sequence. So it learns how to pronounce words in English. And with this technique, CNTK gets very close to the best published number on this task. And what does it look like? Well, it's very straightforward, right? Well, okay, so one thing is special because your input and your labels, they now live in different time axes. That's something you have to tell CNTK. And how do you do that? By explicitly creating an axis and passing it in. And we use this custom axis for the input, and for labels, we use a default axis that also exists. And then you run it through, well, a stack of networks. That's the encoder. The decoder runs the thing through also the same stack of networks, but it has an additional function that you pass in that models the additional information that it carries over through the attention model from the input. And then at the end, you have your regular cross-entropy output here. So what is this recurrent LSTM stack? It's exactly what I described before. It's the recursive definition. Here I use a slightly different syntax, so you're also able to define those things as an array. And then at the bottom of it, you have an LSTM. Now, also the LSTM is just written in terms of CNTK primitives. There's nothing special about that. If you were to go through, you can directly take this picture, this is the famous picture of the LSTM, and map it one-on-one to the corresponding lines in the code here. And if you wanted to change it into a GRU, for example, it's very easy. Just make the necessary modifications here, and the rest will just work. OK, so now, this is the resulting network. It has 600 nodes. So I'm showing you this just to show you how complex networks can be, and yet how little code you actually need to describe those. And CNTK can just handle this just fine. OK, so I'm done with the bulk of my material. I just want to give you a bit of an outlook. So what's on our roadmap? The one thing that we really are investing heavily in now is to turn CNTK as into a library. At the moment, it's an executable that you're running for most of the applications. And having it as a library is actually, it gives you a lot of benefits. So one is it allows you to define your network in your favorite language. You don't have to use BrainScript for that. But the second, which is probably more important, is you probably already have a lot of code lying around for dealing with your data. So data reading will become much easier if you are able to just reuse your existing components and then call from your code into CNTK to do the rest. And it also gives you the possibility to do sort of more non-standard SGD variants. For example, in reinforcement learning, you have to interleave your computation with generating new data once in a while, and that will also be enabled by this. We're also working on increasing the expressiveness. There will be a better handling of nested loops, and we will have increased sparse support, which is becoming very, very important for text workloads. Another thing is we're going to push it towards very large models that are so large that they no longer fit into a GPU, or that the activations no longer fit into a GPU. And lastly, Azure is very soon coming out with a GPU SKU that will then also be able to run CNTK. Okay, so in conclusion, CNTK is Microsoft's open source cross-platform toolkit. It runs on Linux and Windows and has bindings for .NET and C++ for decoding. I talked to you about this notion of computational networks for representing your network, which has all these goodies of automatic differentiation, deferred computation, potential for optimization, the automatic techniques that we can deploy for packing data in mini batches, and the resulting potential of speed up that we have there. I described to you the data parallelization techniques of 1-bit SGD and block momentum. And I think it's pretty clear now on how CNTK can just support this wide range of different model types and different scenarios. And lastly, it's production ready. So that concludes my talk. If you want to know more, you can go to the CNTK GitHub website. All the source code, everything is there. Again, it's under an MIT license. Okay, lastly, if you have any question, you can raise an issue on GitHub. That's our current way of asking questions and how you do things, or you can also just shoot me an email. So, thank you very much.
Thank you for the excellent talk. We have some time for questions. Yeah, right there.
Thank you. I am Iram Calvo from Center for Computing Research, Mexico. And I have a question too about the propagation of the gradients, the errors. You say that with 1 bit you are able, by remembering how much are you not transmitting. But what happens if you have this accumulating, which could render an over...
oh, you mean you keep accumulating and it piles up? No, that wouldn't happen. And the reason is that we dynamically determine the range of the data that we're transferring. So this is done in this particular implementation independently for every column of the matrix. So what I do is for every column, I compute sort of what is the reconstruction value for 1 and the reconstruction value for 0. Mm-hmm. And it turns out the easiest way, and also working very well, is to threshold at 0. So you look at positive numbers and negative numbers.
I see.
And I didn't get any further benefit of adjusting this threshold or learning the threshold or something. So basically what I need to do is then I compute the minimum square error estimate of all the positive numbers, and the minimum square estimate of all the negative numbers. And turns out those are just the means.
Okay.
So what is that? Just transmit the means of all the positive numbers and the means of all the negative numbers.
Right.
And that automatically prevents the problem that you described.
Okay, thank you.
It costs a little bit of extra data. I mean, you're sending maybe 2048 bits plus another, 64 bits for 2 floating point numbers.
Just once.
Yeah.
Right.
Well, no, you do it in every time and for every column, but it's a small percentage of the overall data.
Okay.
So it's not a big problem.
Okay, thank you very much.
There was another question over there.
Hello, I am Fernando Osorio from USP, University of São Paulo. Thank you for your presentation, it was great. And I would like to know about the question, when we work with neural networks, we need to choose the configuration, the number of layers, etc. So you have the Occam razors to indicate that the best network usually is the simplest network in terms of generalization. So what we can do in terms of evolutionary neural networks using these frameworks, so to run different configurations, because you showed only one single network, one configuration.
Right.
And usually we need to run several different experiments, changing the topology, the number of layers, or other
Correct.
parameters.
Yeah, It turns out that unfortunately that is still what you have to do today. There is no really good method of choosing things automatically. There are some techniques for optimizing hyperparameters, for example, but in general you have to run those trainings. You have to run a large amount of training jobs. So what makes that convenient in CNTK is this full configurability, but you really get that from any programming language, right? This is unfortunately what you have to do. And it turns out once you run those kind of experiments, you don't even benefit from parallelization anymore, because it's actually more efficient to parallelize over the number of parameters that you're sweeping over. Sorry, I can't give you a much better answer. It's just a matter, it's a bit of a black art. You have to read papers, you have to talk to people. That's unfortunately still how we do it. Sorry about that.
We have time for one last question.
Yeah, thank you. Fabio González from Universidad Nacional de Colombia. Thanks for the talk, very, very nice toolkit. I got a question about the speed up that you show when comparing to Theano or TensorFlow, which are impressive. Were those with recurrent neural network or sequences?
With recurrent? No, that was a feed-forward neural network.
Okay.
I think on recurrent networks, you might even have a slightly larger advantage because we are able to optimize which parts of the network have to be computed with recurrence and which are not.
Right.
To be really honest, I don't know what Theano does in that area. When I looked at TensorFlow, it looks like it doesn't optimize anything. It treats everything as a separate time slice because you are required to write it in that way, right?
Right.
And you, as a programmer, have a choice to do that by yourself. You can do conversion operations where you batch everything together into one big tensor, perform the operations you can do in one go, and then distribute the data back onto the individual slices.
Right.
But you will have to do that, and it becomes very, very complicated.
Okay, so you expect that with the recurrent neural networks, you will get higher speed up?
Yes, I would.
Okay, and about that speed up, and you mentioned different mechanisms, new mechanisms that you implemented. What's like the one that contributes the most to that, to those speed ups?
Well, definitely the ability to not unroll. That's very important. So I can give an example. When you do the back propagation through an unrolled recurrent network, the early version of the code, let me just see if I can find that. This is going back, right? Oh yeah, there it is. Okay, so if you look at this recurrence here, the original version of CNTK had this parameter inside that loop. So that meant when you ran the back propagation, when you were at this point, you would be back propagating a gradient there and also there for every single time step. And at some point I realized, hey, this is actually not really necessary. We can wait until we have finished this entire loop and then compute this gradient in a single operation. And when I made that change alone sped up the training by 15% relative. So these things are important in the end. And in terms of other speed up, well, obviously the ability to just parallelize, that is the other thing that's really important. And I think another thing you can also just see when you look at the code, the entire CNTK is sort of designed around keeping the GPUs busy. So we try to avoid unnecessary synchronization points between GPU and CPU. We try to make sure that every time the GPU is done with an operation, the next data is there. So for example, data reading is happening concurrently and so on. This is very, very important to do those.
Okay, thank you.
Statements.
All right, we have to conclude now. If you have any other questions, please make sure to catch Frank after his talk. Thanks again.
Thank you very much. You've been a wonderful audience.